Welcome. In this video, we'll tackle a system of nonlinear equations. Our goal is to find all possible pairs of numbers, which we'll call A and B, that satisfy both equations simultaneously. The system we'll be solving is a squared plus b equals 73, and b squared plus a equals 73. Notice a key feature here. The two equations are almost identical. One is just the other with a and b swapped. This symmetry will be the main tool we use to solve it. By the end of this video, you will be able to solve a symmetric system of nonlinear equations. We'll explore two different methods to accomplish this goal, so you can see how different approaches can lead to the same solution. Let's begin with our first method, which leverages the symmetry of the equations. We have the system a squared plus b equals 73 and b squared plus a equals 73. The fact that both expressions on the left are equal to 73 means they must be equal to each other. So we can set a squared plus b equal to b squared plus a. Now our task is to solve this equation for one variable in terms of the other. Let's move all the terms to one side. Subtracting b and a from both sides gives us a squared minus b squared plus b minus a equals 0. This equation has a special form. The first two terms, a squared minus b squared, form a difference of squares. This is a common algebraic pattern. We know that the difference of squares, a squared minus b squared, factors into a minus b times a plus b. Let's apply this to our equation. Substituting the factored form gives us a minus b times a plus b minus a equals 0. This looks promising, but the term b minus a is not quite identical to a minus b. However, they are opposites of each other. In other words, b minus a is equal to -1 times the quantity a minus b. Let's substitute this back into our equation to get a common factor. Now we have a minus b times a plus b minus the quantity a minus b equals 0. And there it is. Both terms have a common factor of a minus b. We can factor this out. Factoring out a minus b gives us the expression a minus b times the quantity a plus b minus 1, all equals 0. This is a key step. The product of two expressions is 0. This means at least one of them must be 0. This gives us two separate cases to consider. Our first case is when a minus b equals 0. Our second case is when a plus b minus 1 equals 0. Solving these two simple equations will guide us to the solutions of our original system. Let's first investigate case 1, when a minus b equals 0. Our first case is a minus b equals 0. This is the simpler of the two. If we add b to both sides of this equation, we find that a equals b. This is an important insight. This case tells us that any solution pair AB must have equal values. Now we can substitute this condition back into one of our original equations. Let's use the first one. The first equation is a squared plus b equals 73. Since we're assuming a equals b, we can replace every b with an a. This will give us a single equation in terms of a. The equation becomes a squared plus a equals 73. This is a quadratic equation. To solve it, we need to set it to 0. Subtracting 73 from both sides gives us a squared plus a minus 73 equals 0. Let's check if this is easily factorable. We're looking for two numbers that multiply to 73 and add to 1. 73 is a prime number, so its only factors are 1 and 73. No combination of these will add to 1. This means we must use the quadratic formula to find the values for a. The quadratic formula is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. In our equation, a squared plus a minus 73 equals 0. The coefficient a is 1, b is 1, and c is negative 73. Let's plug these values into the formula. We get -1 plus or minus the square root of 1 squared minus 4 times 1 times negative 73, all over 2 times 1. Now, let's simplify the expression under the square root, which is called the discriminant. 1 squared is 1, and -4 times negative 73 is 292. So the discriminant is 1 plus 292, which equals 293. This gives us our two solutions for a in this case. Since we know a equals b, we now have our first two pairs of solutions. Our first solution is a equals b equals -1 plus the square root of 293, all over 2. And our second solution is a equals b equals -1 minus the square root of 293 all over 2. We've now found two solutions. But remember, we had a second case to explore. Now let's examine case 2, when a plus b minus 1 equals 0. Our second case is a plus b minus 1 equals 0. From this, we can express one variable in terms of the other. For instance, we can say that b equals 1 minus a. This gives us a relationship between a and b for this second case. As before, we'll substitute this back into one of our original equations. Let's use the first one again. A squared plus b equals 73. We'll substitute 1 minus a for b. This substitution gives us a squared plus 1 minus a equals 73. This is another quadratic equation, just like in case 1. Let's rewrite it in standard quadratic form. A squared minus a plus 1 equals 73. To solve it, we need to set it to 0. Subtracting 73 from both sides gives us a squared minus a minus 72 equals 0. Let's try to factor this one. We need two numbers that multiply to negative 72 and add to negative 1. After a bit of searching, we find that negative 9 and positive 8 work perfectly. So the equation factors into a minus 9 times a plus 8 equals 0. This gives us two possible values for a, 9 or negative 8. Our solutions for a are a equals 9 and a equals negative 8. For each of these a values, we need to find the corresponding b value using our relationship b equals 1 minus a. This is a crucial step. We use the specific relationship for case 2. First, let's take a equals 9. If a is 9, then b is 1 minus 9, which is negative 8. This gives us our third solution pair, 9, 8. Now, let's take a equals negative 8. If a is negative 8, then b is 1 minus negative 8, which is 9. This gives us our fourth solution pair, par 8, 9. Notice how these two solutions are related by swapping a and b. This is another consequence of the system's symmetry. So, by factoring the difference between the two equations, we found a total of 4 solution pairs. But how can we be sure they all work? Let's use our second method, a subtraction method, to check. In this method, we simply subtract the second equation from the first. Our system is a squared plus b equals 73, and b squared plus a equals 73. Subtracting the second equation from the first, we get a squared plus b minus the quantity b squared plus a equals 73 minus 73. The right side simplifies to 0. Now let's distribute the negative sign and rearrange the terms. This gives us a squared minus b squared plus b minus a equals 0. Look familiar? It should. This is the exact same equation we arrived at using the factoring method. Because this equation is a direct consequence of our original system, any pair AB that satisfies the original equations must also satisfy this equation. Conversely, any pair that satisfies this equation gives us potential candidates for our solutions. The next step is the same as before, factor and solve. We've already done this, and we found 4 potential solutions. We've now identified 4 potential solution pairs for the system. It's always a good idea to perform a quick check, especially for nonlinear systems. Here are the 4 solutions we found. Let's check one of the simpler integer solutions. We'll use the pair 9 to 8. We're testing the pair a equals 9, b equals negative 8. First, let's check the equation a squared plus b equals 73. Plugging in the values, we get 9 squared plus negative 8, which is 81 minus 8, which equals 73. This equation holds true. Next, let's check the second equation, b squared plus a equals 73. Plugging in the values, we get negative 8 squared plus 9, which is 64 plus 9, which equals 73. This equation also holds true. Since the pair 9, 8 satisfies both equations, it is indeed a valid solution. The symmetry of the system ensures that 8, 9 will also be a solution. This gives us confidence that our other, more complex solutions are also correct. Let's quickly recap what we've accomplished and the strategies we used. We successfully solved a nonlinear system of equations by recognizing and using its symmetry. We used 2 main methods, which ultimately led to the same result. The first was a direct factoring method, where we set the left sides of the equations equal to each other. The second was a subtraction method, which subtracted the second equation from the first. Both methods produced the key equation a squared minus b squared plus b minus a equals 0. By factoring this equation, we broke the problem down into 2 simpler cases, a equals b and b equals 1 minus a. Each case yielded 2 solutions. So we found a total of 4 solutions for this system. Today, you've learned how to identify and exploit the symmetry in a system of nonlinear equations to find its solutions. This is a very powerful technique in algebra. Thank you for watching.